And we'll get on the current slide. I guess we will get on the current slide. Okay, couple of announcements I wanted to make before we, it's still trying to do something. But we are recording, so let me go and get these said. All right, we have class today. We have class Monday, okay? Monday, okay, let's go over it. Today, I received another paper in, which brings this class total to maybe 4 out of 11, so that's not too good with only 1 day left. So please get papers in. If you get it to me today or tomorrow, you get credit for, you get your bonus point. If you get it to me Monday, you just get your score, no bonus points, okay? Seems like I said something early in the term about not putting things up, but no, that must not have been me, somebody else. Okay, then Monday will be the last day of class, and in addition to receiving all those papers that haven't been turned in early, I will be...
Well, you have papers for English and then a paper for math, and English takes priority.
Yeah. All term long? 10 weeks worth? Okay. But the other thing that happens Monday is I return all your tests to you. Now, the test 1, I'm still missing 1, 2, looks like 2 tests, okay? And test 2, test 2, I think a couple of people have turned that in. I don't have them graded or recorded yet, but they have turned them in. By the way, yesterday was our unit hearing, our planning hearing, and that took every spare moment I had last Friday, over the weekend, and yesterday morning. I thought I had everything done, but one guy hadn't turned in his documentation. He turned in the numbers to me, and he said, I'll get them to you next week. Well, he didn't. I went over there. First thing, had to cancel my my differential equation class so I could collect them. He got there late, but he finally got them in late, but he did get them to me. So, but that took up all morning, and then in the afternoon, I had my physical science class, and then when that was over, I had started getting everything ready for the last of the term, which is egregious. Okay, but anyway, those things are moving well now. So I'll try to get everything graded this weekend. I have no time, 0 time today to grade, but hopefully tomorrow between 10 and 12 and between 3:30 and 5:15, I'll be able to get at least some progress made on all this grading, and then I'll take it home over the weekend. And I've got, especially if we have any rain happens, I'll have some indoor time that I can get some stuff done. Yes?
So, what time will you be in your office?
Tomorrow? I'm in the office from 10 to 12 and from 3:30 to 5:15. I'm on campus from 7:45 until 5:15. So if you come sometime when I'm in class, you can slide it under my office door. Do you know where my office door is?
Yes, sir.
You do? Okay. All right. Down the hall, the very end, just before the stairwell. So down and out, or up and in. Okay. All right. Good deal. Any other questions? Okay. Yeah, this is where we left off last time. I believe this is example 4. If there's no questions. Boy, the computer is not responding well at all today. Okay. Example 4. Okay, well, we won't talk about it. Find the points of inflection of... Got to find my pen here. Okay, there it is. Okay. Find the points of inflection of this function. F of x is equal to x to the 5/3 power. Okay? Now, tell me, how do we find points of inflection? Second? Okay. Yes, that's always a good answer. It's not absolutely complete yet. What derivative? Second derivative. Take the second derivative of the function, and then you do what? Either set it to 0, or where it does not exist. You're absolutely right. And that will be the places you consider for points of inflection. They may not exist, but you still consider it. So let's do as you said and take the first derivative of this function. And what would that be? F prime of x will be what? Five-thirds x to the 2/3 power. Good. Okay? And if we were looking for critical points, this is where we would stop and proceed from there. We're not. We're looking for points of inflection. So we continue, and what's the F double prime? All right. I've got time. We're only next to the last day of class. I think we'll make it before 10/9. 2/3 times 5/3 is 10/9 x to the negative 1/3 power. All right, good deal. All right. Any problems seem to arise here? There we have our second derivative. What would we do first? Besides welcome to you. Why did we take the second derivative anyway? Because I told you to? No, that's not good enough. What's that? And how do we find it once we had the second derivative? Oh, set it equal to 0. So let's try that. Now, in order to set it equal to 0, I think I want to write it in without the negative exponent. Is that all right with you? Okay. So I know a 10 will be on top, a 9 will be on the bottom, and because that's x to the minus 1/3, that moves it downstairs and makes it x to the 1/3 power. And then we want to set that equal to 0. When is that rational form equal to 0? What makes a rational form equal to 0? All right, Lauren's here. Good. Find you. There you are. Okay. What makes a rational expression equal to 0? What must be true? Give me a fractional form that's equal to 0. Any fractional form equal to 0. Say again? 0 over what?
1.
Anything. 0 over 1 is equal to 0. 0 over 55,483 is equal to 0. In order for a fractional form, a rational expression, to be equal to 0, what must be true? The numerator must equal 0. And how often is 10 equal to 0? Never. So this has no point at all where the second derivative is 0. So are we through? Please don't say yes. What else do we consider before that? We've got to have a point. If the second derivative is not equal to 0, what one other condition do we consider? Where the second derivative does not exist. That's the other thing, okay? Is there any place at all where that second derivative does not exist? Where would that be, if there is such a place? What would keep something from existing? What are 3 things you can never do in mathematics? Divide by 0. Is there any case for your fractional form there that would make that denominator equal to 0? At x equals 0. So there's a candidate, x equals 0, where it does not exist. Okay? It's the only place where the denominator can be 0. The other 2, by the way, are where radicals, even indexed radicals, are negative. Well, this is an odd index. This is a cube root of x. That can be positive or negative. No problems there. And the third that we've hit so far is where log would either be 0 or negative. This has no logs in it. So we're perfectly happy the way it is. We found one and only one candidate as our inflection point. Now we've got to do what? Okay, we consider it on either side. So let's go to, which side do you want to do first? The left, okay. The left, that's the negative numbers. What is a good, reasonable negative number to plug in for your, here, f double prime of a good negative number? Negative 1 sounds like an excellent negative. What would that be? 10 over 9 times the cube root. I'm writing this not in fractional exponent, but in radical form, a negative 1. What would that give us? What is the cube root of negative 1? I'm sorry?
Would that be I?
No, square root of negative 1 would be I. Maybe we could make it another number, like j. No, I'm just kidding. Okay. Can you take the cube root of negative 1? That seems to be the question here. Can you? Why not? The radicals that you can't do are only the even indexed radicals. Square roots, fourth roots, sixth roots, eighth roots, those. Odd, you can do it. There's no problem in taking the cube root of negative 1. What would it be, though? What number multiplied by itself 3 times would give you a negative 1? Negative 1 times negative 1 is 1 times another negative 1 would become negative 1. That does have a cube root. So if that's negative 1, this would be negative 10/9. All right? Except for taking the derivatives, we haven't done much calculus at all with this. It's all been algebra, okay, mathematics, okay. Now, we've done something to the left. We found out the second derivative there is negative. That means what about it? The second derivative is negative. What does that mean about the function, the graph of the function? Really? Okay. I thought that had to do with first derivatives, critical values. It does contribute to it, but not by itself. You can't determine that. It would be heading toward it does look like it's heading toward a local maximum. You're right there. But what is it about a second derivative? What do we learn from a second derivative? We're looking at points of inflection. What does a point of inflection tell you? What the second derivative tell you? I know it was a long time ago. It was Monday. 2 days. Goodness gracious, that's a lifetime, isn't it? For an ant. Okay. What does the second derivative? First derivative tells you slope of a tangent line. What does second derivative tell you? Oh, a long time ago. Okay. Let your eyes flick back to the page right before the one we're looking at and look at Theorem 1. Test for concavity. That's what the second derivative tells us. Okay. Must have really gotten that point across well Monday, okay? Now, what does a second derivative of negative 10/9 tell you about concavity? Say again? A little louder. That it exists? Is that what you said? No. I can't. It doesn't exist? No. Concavity.
It's going up, right? No, it's going down.
Okay, the concavity is down. The function's increasing. That's what the first derivative tells you. Whether the rate at which it's increasing, that's what the second derivative tells you. And it's concave down if it's negative. Okay, concave down means it's curving downward. Okay? What do we do next?
The right side.
Do the right side. Can you give me a decent point somewhere on the right side of 0? That would be greater than 0? 1! All right, let's try 1. F double prime of 1. And what would that be? 10 over 9 times the cube root of 1. We had a lot of discussion about whether negative 1 had a cube root. Does positive 1 have a cube root? Yes. What would it be? 1. Okay, so what would the F double prime of x be, of 1 be? Positive 10 over 9. Okay, seems like we've seen that somewhere before. Okay, what does that tell you? Oh, wow, yes, it's concave up. It's all coming back to me now, okay? So if it's concave down to the left of your potential inflection point and concave up to the right of it, what does that tell you? It is an inflection point. An inflection point is where the concavity changes, okay? What does a change in sign of the first derivative tell you? Oh no, we're not talking about that now. We're talking about second derivatives. We don't need to remember that, do we? What does the change of sign of a first derivative tell you? Okay, the critical point is where it's 0 or undefined, okay? The first derivative. And what does the sign of the first derivative tell you? If it's positive, it's first derivative is positive, the function is increasing. If the first derivative is negative, it's decreasing. So if you have a change of sign of your first derivative, that tells you you've got could be, but first derivative doesn't tell you about concavity. What's that? A local maximum, or if the first derivative is negative to begin with, approaching a critical point, and then past the critical point is positive. Minimum, a local minimum. Okay, very good. And same thing for second derivatives, only you're looking at something else. you're looking at find your point of inflection, or let me call it this, potential point of inflection, okay? That potential point of inflection will be where the second derivative is 0 or doesn't exist. And then you test on either side of that, but don't go past the next point of inflection if you got one. Test on either side of that and see. And if you have a change of concavity, then you do have a point of inflection. If you don't, if it's concave down on either side, it's not a point of inflection. Or concave up on either side, not a point of inflection, okay? But if you do have a change of concavity on either side of that potential point of inflection, then it does make it a point of inflection. All right. Okay. And sure enough, that's what we see here. Concave down to the left, concave up to the right, because it was negative to the left, positive to the right. At the point in question, x equals 0, that must be a point of inflection.
So let's say if the point of inflection was up at 1, that means it would not be a point of inflection.
Okay, say that one more time.
So you know how the point of inflection is right now at 0?
Right.
What if it was up at 1?
At 1. Okay, now.
At the in the y
Right here?
y-axis.
Okay.
It was right there. Would that make
You mean the whole function was up there?
Yeah.
Okay, yeah, that'd still be a point of inflection. If it was shifted this way and this part was there, that wouldn't be a point of inflection because your second derivative would be positive there, because it would still be like this. But if you still had the change of your second derivative was undefined at 1, yeah, you test that, and if it was, negative concave down here, concave up there, then it would be a point of inflection. Okay. See, we had a name for the other critical point, critical values. We don't have a name for this except a potential point of inflection. So, there's a little graphical insight here. Points of inflection are easy to spot on a graph of the first derivative f prime. If f double prime of c is equal to 0 and f double prime changes sign at c, then the increasing decreasing behavior of f prime changes at c. Thus, inflection points of f occur where f prime has a local minimum or maximum. Where f prime has a local. Okay. Now, what that means, you have to draw a bunch of graphs, okay? The whole purpose for doing the derivatives is so you don't have to do it. You can figure it out analytically. So plugging in values to me make a lot more sense than doing lots of graphs. But this is what they're getting at, and I will blow this up so you can see it. But who wants to draw all this many graphs, okay? I don't know. Y'all may love drawing graphs. I don't particularly. Okay? Especially you've seen me draw graphs. You know how bad I am at it. If this is your function here, y is equal to f of x, and you're trying to describe the behavior of it, the first thing you would do would be what? One of those questions. Take a derivative. And what does the first derivative tell you? Has potential to tell you. First derivative tells you about potential. In fact, you named it earlier. Critical points, critical values, exactly. And where would you, just describe to me where you would expect to see a critical value here? Where you have a local minimum, where you have a local maximum, and where you have the local minimum. You would expect the critical value there, there, and there. What would be true about those values right there? That first derivative. Say again? Yeah, the first derivative is 0. The slope of the function is 0 there. First derivative is 0. That gives you your critical values. Or the other condition would be where the first derivative does not exist. It looks like it exists everywhere here because this is a smooth function. for it to not exist, you're not going to have a smooth function. You're going to have a cusp or a corner or something. It's not going to be very smooth. This one is not going to have a do not exist anywhere where we see it. So we got our, and we test once we get f prime equals 0 here, here, and here. Actually, here, here, and here. Those are critical values. These are the critical points. We test the first derivative to the left, and that would tell you it would be heading down, which means the first derivative would be negative, and we would test to the right, and you'd find it was positive, so you knew that you had a critical value there. If the first derivative changes signs of that critical value, you have a max or min. Which do you have? Because it's negative here, positive there, that has to be a minimum. You go to the next critical value. You've already tested a point in here and said that its first derivative is positive there, so you check a point somewhere over here to the right of that critical point, and what do you find out? Say again? It's negative. So you had another change of first derivatives at the critical point, so that means you have another local extrema, and this would be a local maximum. Okay. Okay. So we've already tested here and found that the function had a first derivative negative here. We know it has a 0 there. So where do we test? Somewhere to the right. And what do we discover? First derivative is positive, so therefore that means that is a local minimum. Because it is that negative to the left, positive to the right, stand up, sit down, fight. No, okay. Now, next we do what? We did all that with the first derivative. Now we do what? Take a second derivative. We do that, and what do we test for? Say again? Okay, yeah, but what is the second derivative? What's the two things we look for when we find that second derivative right at the beginning? Okay, that potentials for that. How do we determine that it might be a potential point of inflection? What about the second derivative would have to be true? It doesn't exist, or second derivative equal to 0. And what they did, they plotted the first derivative. Okay, I didn't want to draw the first graph, okay? I want to do it all analytically, and you can't. But when you draw the second graph, we find that the second derivative was 0 here and there. There were no places where the second derivative was undefined, because that's a nice smooth graph. This is a nice smooth graph. So there's no points of undefined second derivative, but there are two places where the first derivative was 0. And then what do we do? Yeah, pick something to the left of that potential point of inflection. Up here we could call them critical points or critical values. Here we don't have a name for it. Potential point of inflection, and we test to the left, and what do we find to the left? Second derivative is positive here and negative there, which means it's the function. This is the derivative. The function is concave up here and concave down there. You do have a change of second derivative, so therefore that is a point of inflection. If it was the same on both sides, concave down and concave down, or concave up and concave up, or concave down and concave down, it would not be a point of inflection. But this one is. Okay? And then we go to the next one, find a local minimum on your first derivative, which means the second derivative is 0. And then we look to the left and right. We already know here it's concave down. Look to the right, and we find that's a positive second derivative. So it's concave up. Okay? If you went to draw the graph of the second derivative, why bother? All you have to do is plug in. But if you did draw the graph, you see that you do have the second derivative is 0 here, here for the first derivative and here on the second derivative, 0 there and there. So therefore it is a potential point of inflection, and because the second derivative was positive here, negative there, then that is a point of inflection here, negative here, positive there, that is a point of inflection there. But you don't have to draw even one graph. You can do it all analytically, analyzing your derivatives. That's the whole point. Okay. So, that's kind of led us to something else, and I think one was being psychotic. I can't remember the word now. Looking ahead, okay, when he said this. Actually, the easier way, rather than testing on your first derivative, testing to the left and testing to the right, that's a little bit of work, not hard work, but a little bit of work. But if all you have to do is, I'm surprised there's no graph here, all you have to do is go on and take your second derivative. And guess what? If that second derivative at your critical point is, say again? Okay, you're not interested in 0 here. What you're trying to determine is maximum and minimum. Second derivative of 0 or not does not exist. That determines points of inflection. But you can also use the second derivative to tell you about whether it's a maximum, a minimum, or neither. Because guess what? If you have a first derivative of 0 here, you know that, then all you have to do is take the second derivative at that same point. And what are 3 conditions that you could have for a second derivative? Dealing with signs. It's Sagittarius. No, not those signs. Okay. Never mind. What 2 signs could it have? Positive or? And then what's the other option? 0. Okay. So, here we know the first derivative is 0 at this point. We don't know what the curve looks like there, but it's 0 there. Okay, let's take the derivative at that same critical value. Okay? Now, what are those 3 possibilities for the second derivative? The signs? Positive. What would that tell you? Second derivative positive? Oh, how soon we forget. Concave up. Well, guess what? If it's concave up at that point where the first derivative is 0, what does that tell you? That's a minimum. It's got to be because it's moving up there. Okay? And you know it's a 0 derivative there because first derivative is 0. What's another possibility of that second derivative? Negative. And what does that tell you? Concave down. If you know the first derivative is 0 there and it's concave down there, guess what? Maximum, local maximum. Okay, who needs to go back and check those values left and right anymore for the first derivative? You may still for the second, but not for the first. And then what happens if you find out where the first derivative is 0, you also have the second derivative 0. What does that tell you?
There's no change of signs.
Is what?
There's no change of signs.
Let's see if that's quite true. I don't, well, I think all it tells you is second derivative is neither concave up nor concave down. That's the answer. Okay, then in that case, guess what you have to do? Test. Okay, first derivative is 0 there, and second derivative is 0 there. All that second derivative tells you is neither concave up nor concave down, so we don't know what it's doing, so that's where you have to test it. Okay? It would be nice, and that's why it says, well, let me blow this up. I kept it small so you couldn't read it. because those are exactly the questions I was asking, weren't they? Okay. If that first derivative, okay, if C is a critical point means the first derivative is 0, okay? And if, rather than testing to the left and right, then just take the second derivative at that same value. If it's positive, guaranteed to be a minimum. If it's negative, guaranteed to be a maximum. Okay? But if it's 0, you can't tell. Inconclusive. It may be a local minimum, maybe a local max, or it may be a neither. Okay? You're just going to have to plug and chug. Test it to the left, test it to the right. And you can either test the first or second derivative there and find out. Okay? Make sense? Okay? Now, that was theorem 3, second derivative test. Okay. Here's the graph that was on the previous page. That's what I was looking for, and I didn't see it. Okay. This is looking at it from the other way. If you have a graph here, and you know you have a local maximum there, right? What does that tell you about the first derivative there? First derivative there. Local maximum there. First derivative would be, one more test. It's a local maximum there. What does that tell you about the first derivative? 0, because it's a horizontal tangent line there, right? No slope, 0 slope, okay? And if that's the first, if that is a maximum, you know it's a maximum, guess what? You also can look at that and tell it's concavity. Second? Concave down, which tells you what about the second derivative? Negative, exactly. Now, if you know this is a minimum here, somehow you know it, okay? What does that tell you about the first derivative there? 0. What does it tell you about the second derivative there? It's positive because it's concave up. You're absolutely right. Concavity determines the type of critical point. And that's what the third theorem said, but they gave you the theorem before they gave you the graph. Sorry about that. Now, our text has a strange little drawing I've never seen anywhere else. Okay, I think I'll put it on this one. That means nothing. It's just a localized place of this graph. And if this graph is going up, in other words, a local minimum, what does that tell you about the concavity on the left? Positive. And on the right? Positive also. So you have a little smiley face. Isn't that cute? Okay? I've never seen this before in a calculus text. It wasn't in the previous edition. Now let's take a localized portion of the graph here. And what if it's this? Okay, and what would that tell you? Negative and negative. So sad, isn't it? Okay. Brightly positive. Okay. Dorky. No, I'm sorry, I didn't say that. Okay, let's move on to example 5. All right. Analyze the critical points of this function right here. Okay? F of x is equal to 2x minus x squared times e to the x. What's the first thing you're going to do? It says analyze the critical points. Take a first derivative. Sounds like a capital idea. F prime of x would be what? Or what are we going to have to use here? Can you read it? Okay, you want me to write it again? Would that be helpful? What rule are you going to have to use? A yardstick. No, that's not it. Second, a product rule, exactly. And what does the product rule tell you? Derivative first, which would be? Okay, a little bit louder, I can't hear.
The first would be the one inside parentheses, right?
That looks like the first one to me, yeah.
So it would be 2 minus would that be 5x?
That's a 2.
2x to the square root of 2x.
Say that again.
Minus 2x.
Minus 2x, I got it, okay. We'll put that in parentheses, times what? E to the x, that's the second one. And then what? Plus. Say again, e to the x times 2x minus x squared. Okay, she rearranged orders, but that's perfectly fine to do. Okay. Now, why would we take a first derivative anyway? Why would we do that? Because I asked you to.
We're trying to find the critical point.
Okay, and how does the first derivative relate to critical points?
That's equal to 0.
Either equal to 0, so let's set this equal to 0. Okay, let's try that. All right, don't you think we can smooth this up a little bit? I know I can factor out an e to the x, would you think? And that's going to leave us with a 2 minus, I'm sorry, goodness gracious. Okay, just looking at this, that's going to be a 2 minus 2x plus 2x minus x squared, right? If you factored out the e to the x and put those together, wouldn't you have that? Okay, what does that tell you? How can you simplify that?
E to the x times x squared.
Okay, the minus 2 to the x plus 2 to the x adds a 0. Okay, so that would just be a e to the x times 2 minus x squared is equal to 0. Okay. Now what? That would lead us to think that either what? You may have said it right, I just can't hear well.
One of those, both of them equal to 0.
So each equals 0, is that what you, okay, yeah. Either e to the x is equal to 0, or 2 minus x squared is equal to 0. Is that what you said? Sounds like a great thing to say, okay? Now what? When is e to the x ever equal to 0? Say again?
E equals 0.
Well, e is a number. It's an irrational number. It's 2.7 blah, 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 blah. Is that ever equal to 0? Not in this universe. Okay, now, so, and what values of x would make e to the x equal to 0? Okay, e to the 0 is 1. Anything to 0 is 1. So x equals 0 wouldn't work. Any others? Say again. Well, no, it's not undefined. There are no values. No values. If you drew the function of e to the x, okay, e to the 0 is 1. We've already said that, right? And when x gets negative, it's approaching 0, but never gets there. And positive, it just gets larger and larger and larger. There are no values where e to the x is equal to 0. So this will not produce a critical point. Okay? Can't happen. Okay? How about the other one? What could you do there? You could. Let's do that. And what would that give you? Okay. And then what? I don't like taking square roots of negative numbers. It's just something I don't like doing. Oh, okay. Let's multiply or divide by -1. Okay, we can do that. And you could have taken care of that if you'd added x squared to both sides, but that's okay. We still got there. Now what? Now we can take a square root. Okay, and that would give us x equal to a little louder. Yes, very good. Remember to do plus or minus the square root of 2. Yes. Plus the square root of 2 is going to be about plus 1.414, blah, 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 irrational number. Or negative 1.414, blah, 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 negative number. Okay? So those are your two candidates for, those are your two critical points. Okay? But it says analyze those critical points, right? Analyze the critical points of this function. So that means we want to find out if those critical points produce what are 3 possibilities? Okay, and what would that produce as critical points? Second, local minimum, local maximum, or neither. Exactly. So we want to analyze that. What we could do is pick some points if you like doing that, but much easier would be, most of the time anyway, one of those questions. Take another derivative, make the second derivative of this. So here's your first derivative, and written in better form, f prime of x is equal to e to the x times 2 minus x squared. So I want to take a second derivative, f double prime of x. Can you help me do that? E to the x times 2 minus x squared. You took the derivative of the first times the second, plus e to the x times what? Negative 2x. Very good. And then what do we do with that? Okay, why? You first set it equal to 0. You're looking where, well, no, okay, sorry, you don't even have to do that. Yeah, you're right. Let's factor it out. F double prime of x is equal to e to the x times what? Okay, you like writing that. That's fine. Minus x squared minus 2x plus 2. Okay? Now, we're not looking right now for points of inflection. If we were, we'd set that equal to 0. Right now, we're just seeing what is the nature of those two critical points. So guess what we do? What do you do with Glade? Plug it in, right? Okay, so let's do that. Let's do f double prime of, what you want to do first? Okay, square root of 2, and that would be e to the square root of 2 times negative. And what is square root of 2 squared? 2, okay. Next, minus 2 root 2 plus 2. What can you do to simplify that a little bit? Second? Plus 2 minus 2, add to 0. Very good. All right. All we're doing is analyzing this. Okay? All we're doing is analyzing. What are we analyzing it to see what it is? Positive, negative, or zero, right? Now, what is e to the square root of 2? Okay. Okay, yeah. It's e to the, I don't know, 1.5 power. It doesn't matter. There's the graph of e. What is e always? Positive. Okay, so this factor is positive. How about this? Negative 2 root 2. It's negative, obviously, it's negative. And what you get when you multiply a positive times a negative? A negative. So right there it tells you the second derivative is negative. And what does that tell you? Okay, what? Oh, really? Oh, we've rewritten that. I'd forgotten that, okay? Concave down. And let's see, at square root of 2, sure enough, look at that, it's concave down. You didn't have to test points anywhere. All you had to do was look at your second derivative. You don't have to evaluate it, just tell what sign it is. Okay, let's do the same thing for negative 2. F double prime of negative root 2, and that would be what? E to the negative root 2 times okay. All right. Let's get what we're doing now. It's negative times the it's negative times negative root 2 squared. Do the negative root 2 and square it, and what do you get? Say again? Positive 2, and then you negate it, and that gives you? Yeah, you see the first negative is this one. That's what you square, and then you negate your answer. So that still gives you a negative 2. Okay? Okay, and then what would be the next one? Minus, I'm going to erase some stuff because it's in my way. Get out of my way. Okay. Okay, and what would that give you? I'm sorry. Negative 2 times negative root 2, right? Plus 2. And again, these add to 0. But what does this give you? A positive number. How about e to the minus root 2? What would that give you? Would it? All right. Forgot we wrote that one too. Okay. Here is e to the minus x. Okay. Give me a different color. Red. Okay. Yeah. Warning, warning, warning. Okay. E to the minus x would be something like that. You just flip it across. And guess what that is? Always positive. So this is positive, and we determined that was positive, so guess what? Second derivative is positive at negative root 2. And what does that tell you? Concave up. And what does that tell you about your critical point? A what? I couldn't hear. Okay. A local minimum. If it's concave up, it's local minimum. You're absolutely right. And it also means Davis is here. Okay. Two things it means. Okay. All right. So I didn't ask that other question, but at positive root 2, analyzing the second derivative tells you it's negative, meaning it's concave down, meaning that's a local maximum. And at negative root 2, we found the second derivative is positive, meaning it's a local minimum. You didn't have to test points anywhere. Now, frankly, on this problem, it's been really easy to test 1 point. 0. Okay. So all you had to do, I erased part of that. I didn't mean to. Whoa, let's get the red out. Okay. If we'd have plugged the 0 in here, we would have gotten 1 here and 2 here. We would have seen that's a first derivative positive there. So that tells you it's increasing here. You still have to pick 2 more points to do, so still I think maybe second derivative is easier than picking points. But that one point was really easy to do. But the other points, it's going to take a little more work. Okay, but not much. I would pick 2 and -2. They would be pretty easy. But usually the second derivative is easier. Okay. All right, any questions on that? That was example 5. Let's move on to example 6. We're on page 220, chapter 4, application of the derivative, section 4.4, the shape of a graph. Okay? And here's example 6. Analyze the critical points of this function here. F of x is equal to x to the 5th minus 5x to the 4th. I think this will be easier. You don't have any product rule that you have to deal with, but it's going to be pretty easy. So what do you do first? It says, analyze the critical points of that graph. What do you do? First step. Take a derivative. So f prime of x would be what? Help me. Page 220, chapter 4, section 4.4. 5x to the 4th minus 20x, what? Cubed. Got it. Okay. And what do we do with that first derivative? Set it equal to 0. Sounds like a capital idea. Now what do we do with that equation? Second? Well, we don't have factors yet. Those are terms. Oh, let's factor and make them factors, okay? And what can you factor out? 5x cubed. And what does that leave you with? X minus 4, 3, 2, 1. Okay. Done. And set that, and that's equal to 0. Now, what do we do? Okay, and what would that be? 5x cubed equals 0, or x minus 4 equals 0. What does the first one give you? X equals 0. That's the only way you can get a 0. That's a 5 times a x times a x times a x equals 0. 5 can't be 0. X would be 0, or x would be 0, or x would be 0. Okay, so that would be x equals 0. Or x equals 4. So here are our 2 critical points. Only 2. We could have had up to 5 of them, but we only have, well, maybe only 4, but we only have 2. Okay? It says analyze them. So what does that mean to you? You're determining whether these critical points are local maximum, local minimum, or neither. Right? Okay? So how are we going to tell that? Take the second derivative. Sounds like a capital idea. So what is f double prime? A little louder, I can't hear.
20x cubed.
Okay, yeah, I would use this one here. 20x cubed.
X
60 squared. Okay. Now, time out here. Well, what would you want to do next? Yeah, I was going to say you can either factor that and make it simple to look at, or just plug in those 2 values. That's all you're really interested in. So f double prime first at 0 is going to be 0. What does that tell you? Say again?
It doesn't change, so either.
Let's go back to our theorem, unless it's changed. What is the second derivative of 0? Inconclusive. It doesn't tell you anything yet. Okay? So it looks like what we're going to have to do is do some plug-in for that. Okay? We throw out the first one, the other one too, or do you want to try that? F double prime at 4. And what does that give you? Bless you. 20 times what? Oh, you already did it?
Yeah.
What did you get it? 220? 320? Is that what you said? I can't hear well. Okay, plugging in a 4. 4 would be 8. 8 times that would be 160, right? Minus, and 4 squared is 16 times 6 is, woo. Did I do that wrong? I think I must have. 4 cubed, oh, 4 cubed is 64. Sorry about that. 64 times 20, goodness gracious. 1, 2, second? 1,280. Okay, minus 60 times 16. Second? 900. Okay, that's all I have to do. What does that tell you? Second derivative is positive. That tells you what? Local minimum. Very good. So that we know is a local minimum. The other one we have to test. So let's pick something to the left of 0. What could that be? Like a -1. And let's do our first derivative. We don't have to do the other. So f prime of -1 is five. Second. Minus 20. F prime at -1. -1 cubed is? -1, okay? And this would be 25, okay? Positive, okay? So that tells you the first derivative is increasing to the left of 0. And then what other would you might choose? Second? F prime of 1. Okay, that sounds reasonable. What would that give you? Second? -15? Yeah, 5 minus 20 is -15. Who cares what it is? It's negative. Positive to the left, negative to the right. Stand up, sit down, fight, fight, fight. What does that tell you? Positive to the left, negative to the right. Maximum, of course. Okay, because it's increasing to the left, decreasing to the right. It has to be a maximum there. The second derivative didn't give you enough information there because it was 0. So there you have to go back and use your right and left test. Okay. So we found that all we had to do was find what the critical points were. We did. And what they were, local maximum, then a local minimum. Very good. All right. They have a little summary here. That's the table that you see in the summary. I'll blow that up for you if you want to. Here is first derivative. If f prime is greater than 0, that tells you the function is increasing. If f prime is less than 0, it tells you the function is decreasing. If f prime is equal to 0, that tells you it's a critical point. Okay? If f double prime is greater than 0, that means it's concave up. If f prime is less than 0, double prime is less than 0, concave down. If f prime is 0, if double prime is 0, you're not real sure. It could be an inflection point or not, and you have to do further testing there. Okay. Good deal. That ends the section 4.4. Are you interested in doing the preliminary questions? Say again? No? Okay. Then homework exercises will be do number 1. It has 4 parts. Fun to do all those. Then do any of the odds 3 through 17. Then do any of the odds 19 through 25. Then do any of the odds 27 through 39. Any of the odds 41 through 55. Do 57, it's the only one like that. And then any of the either 59 or no, do 59, okay? And then you can look at 61 and 63. They say those are sort of think-through type answers. 65 is a pretty interesting practical application of this, and that's 65. Okay? Then under your further insights and challenges, you can do anything there that tickles your fancy. I usually look just to see if there's a potential paper topic, and since a couple of you have come in since I harped on it before, if you haven't done your paper yet, folks, I will accept it today or tomorrow and give you that 1 remaining bonus point. But if you wait until Monday, you get 0 bonus points. If it's anything after Monday, you start losing points. Okay? So please get your papers in, preferably today or tomorrow. I'll accept them on Monday, and I'll accept them later, but you'll be losing points later. Okay? Any questions? Okay. Now we've been going at it about 1 hour and 15 minutes. I'm about ready for a bladder break. Would y'all be willing to take one? Or whatever kind of break you would like to take. Let me get out of this, and we'll be starting 4.5. And I'll pause. All right. Now, this is the first one. Yeah. Okay. Section 4.5 is a very important section. Okay? The title of it is L'Hopital's Rule. It's an incredibly valuable tool for computing certain limits that are otherwise difficult, if not impossible, to evaluate without using it. Also used for determining asymptotic behavior, limits at infinity. We'll use it for graph sketching in the next section, so there's tons and tons of uses for it. Now, what it starts with is, what if you have a quotient of 2 functions, and that itself is a function, and you're trying to evaluate the limit of that quotient. Now, remember the definition for limit? That would be f of x plus a minus f of x divided by x minus a, or something like that, and then let that go to 0. Well, if that's a quotient, oh man, that can get really, really messy, okay? In fact, almost interminably messy, okay? So, good old L'Hopital, okay? Roughly speaking, L'Hopital's rule states that when f of x divided by g of x is an indeterminate form. What do we mean by that? 0 over 0. That's one of them. There are actually some others. But an indeterminate form, also infinity over infinity. That's also indeterminate. There are actually a couple of others, and L'Hopital's rule works. Now, who was L'Hopital? Named after a French mathematician, Guillaume Francois Antoine Marquis de L'Hopital. Okay, goodness gracious, what a name. Okay, lived 1661 to 1704. Goodness gracious, that's a long time ago. For instance, Georgia wasn't even a colony during that time. Hardly anything was a colony at that time. It was after I think it's after Mayflower, but certainly before, so Virginia and Massachusetts were colonies, and maybe a few others, but not many. We were just barely getting started then. But he wrote the first textbook on calculus in 1696, and he had this rule in there. The odds are he probably didn't come up with it himself, but he was the first one to record it, so it's given his name. So it's L'Hopital. Okay. And this is L'Hopital's rule. All right. Assume that both f and g are differentiable functions. Okay. If they're not, you really can't do much with it. Okay. So assume they're differentiable functions on some open interval containing the number a. Okay. They don't have to be differentiable everywhere, but on this interval containing a, they need to be differentiable. And let's just assume that at that point a, f of a and g of a are both equal to 0. Okay? Let's also assume that g prime of a, or g prime of x, is not equal to 0, except possibly at a. Okay? So the g prime cannot be, because g is in the denominator. Then here's what L'Hopital's rule says. The limit as x approaches a of f of x over g of x. Now remember, the good old limit law said that the limit of a, let's just plug and check. When you plug in x equal a here, f of a over g of a, those are both 0. 0 over 0 is an indeterminate form. So L'Hopital's rule says, surprise, surprise, all you have to do is take the first root of both the numerator and denominator, they are differentiable functions, and then take the limit of that. And that should be the same limit as this. Really? Why? Now, it only works if these two are both 0, or both infinity. If the limit on the right exists, this one exists, or is infinite, that could be either positive infinity or negative infinity, then this is true if the limit on the right exists or is infinite. The conclusion also holds if f of x and g of x are differentiable for x near but not equal to a, and that the limit as x approaches a of f of x is either plus or minus infinity, and the limit of x approaches a of g of x is plus or minus infinity. So 0 over 0 would use L'Hopital rule, plus or minus infinity over infinity use L'Hopital's rule. Furthermore, the rule is valid for one-sided limits as well. Okay? So, let's do the first. Wow, okay. Gonna be a time before we get to that. Let's do example 1. Use L'Hopital's rule to evaluate the limit. Ooh, let's get my pen back. Okay. Going to evaluate the limit. And you thought you were through with limits, didn't you? No way. Okay. As x approaches 2 of x cubed minus 8 over x fourth plus x plus 2x, sorry about that, minus 20. Okay? We want to evaluate that limit. What's our first step to evaluate a limit? Plug it in, plug it in. Let's see what we get. When you plug it, yeah, the numerator becomes a 0. Okay? That means either this limit is 0 or it's an indeterminate form. Let's see. Plug in x equal 2 here. What do you get? Is that a 2 or a 4? 4. It is a 4. Okay. 2 to the 4th power is 16. Plus 4 is 20. Minus 20 is 0. 0 is 0, indeterminate form. Now, do you want to try doing the limit rule? You know, I don't. But L'Hopital's rule, I don't mind that at all. What does that tell you we would want to do? Okay, the limit as x approaches 2, that doesn't change. Take derivative of the numerator, and what does that give you? 3x squared. Done. Second? Oh, you're going to do something else, okay. All right. 4x cubed. I need a sign. Give me a sign. Okay. Plus 2, okay. All right. Now, let's take the limit of that. What's the numerator give you? 12 over 34, is that what you said? Yeah, 34. Okay. Let's reduce that. 6 over 17. Oh, I do that, didn't I? No, it's not very obvious at all, is it? Does have a limit, even though the first is an indeterminate form. Use L'Hopital's rule. Try it again. Sure enough, it does have a limit. 6/17. Yeah, they got it right too. Good for them. Okay? I want to try example 2. The limit as x approaches 2 of 4 minus x squared over sine of pi x. What would you try first? Plug it in. What do you get? 0 over 0. Guess what? Can't tell. Indeterminate. Inconclusive. So what do we do next? Take, well, to the limit as x approaches 2 of the derivative. And what would that be?
2x.
Negative 2x over. Okay, I thought I heard you say cosine of pi x. Was there anything else? Times a pi. Chain rule. Chain rule. Okay. Remember? Derivative of the outer times the derivative of the inner. Okay? All right. Now what? Plug it in, and what do we get? Negative 4 over pi. And cosine of 2 pi is 1. Negative 4 over pi. Oh, wasn't that obvious? It was negative 4 over pi. Perfectly good answer. Weird, but irrational. I mean, not irrational. Yeah, irrational. It was irrational. Okay. How about example 3? Evaluate this one. The limit as x approaches pi halves of cosine squared x over 1 minus sine x. All right. I want to do a little timeout here, okay? That first one, remember before we knew L'Hopital's rule, if we had something like that, what would we try? Factoring. The numerator is factorable, believe it or not. We know that, don't we? Of course we do. Difference between perfect cubes is factorable. However, that denominator, if it's factorable, I sure don't know it right off the top. So L'Hopital's rule is far easier than doing that. The second one, numerator is factorable. That denominator is not. So L'Hopital's rule is just about our only option. This one, however, we could factor. Okay? But before even we do that, what would we do? Plug it in. What would that give us? Cosine of pi halves? 0. 0 squared is? 0. Sine of pi halves is? 1. 1 minus 1 is? 0. So it's a 0 over 0. So this one, believe it or not, you could continue and do by factor. We'll come back and do that later. But let's, since we're in L'Hopital's rule, let's do L'Hopital's rule. What would that tell us? Limit as x approaches pi halves of, okay, negative sine x, I buy that, times 2 cosine x. You know why? Because it's the chain rule thing. The outer function is a squaring function, 2 times cosine times the root of the inner, which is minus. Okay, so you do have a 2 there. Leave the 2 off, you get a wrong answer. Okay, how about the denominator? Does that have a factor? I mean, can you take the derivative of that? Negative cosine x. Okay, well then I can divide out the negatives and the cosine x's. Okay, and what does that leave me with? 2 sine x over 1, and when you plug that in, what do you get? Second? 2. Okay. Now, as I said, on this one, you could have factored. That would be the limit as x approaches pi halves. Now, how's another way I can write cosine squared x, especially in terms of the what's in the denominator, sine? Can I? Oh boy. Second? No. Okay. What? Second?
So the one he was saying is sine 2x.
Yeah, I believe you're right. Okay. What is it? This is anytime you see a square, think Pythagoras. So this is one of those Pythagorean identities. Remember what it is? It's the basic one, or it comes from the basic one. Sine squared x plus cosine squared x is always equal to 1. Okay. Now, if you had a cosine squared x, you want to isolate that, what would you do?
1 over sine squared x.
Say again?
1 over sine squared x.
Oh, okay. To undo addition, you divide. I forgot that. You subtract. Oh my. All right, so you subtract the sine squared x from both sides. Okay, and what does that give you? These go away, and you get cosine squared x is equal to 1 minus sine squared x. Oh, that looks a little more familiar. So what we'll do here is plug that in, 1 minus sine squared x over 1 minus sine x. Right? Now, what can you do with that numerator? Second? Okay, you could plug in and you'll get the same thing you did last time, because sine of pi halves is yes, 1 squared is 1, and 1 minus 1 is 0 over 0. Okay, we still got that. We didn't really change anything here. We just changed the way it wrote. So, what I was suggesting is, what's the F word? Factor. Can that numerator be factored? Need to talk with your Math 100 teacher. How? How can you factor it? Okay, let me give you a hint. 1 is a perfect square. Sine squared is a perfect square. This is a difference of two perfect squares. How does that factor?
Would be sin x.
Second? Okay. What's the only possible factorization for 1? 1. Okay. So it's going to be 1 times 1. Look, the sign of your last term is negative. What does that say about these two signs? One's got to be negative, one's got to be positive. What's the only possible factorization of sine squared? Sine x times sine x. Now that doesn't guarantee that's the right factorization until you pull it and see if it is. 1 times 1 is 1, okay? And outer is minus sine x minus sine x, that goes to 0. Negative sine squared x, sure enough, that is the factorization. All right. And then you divide that by 1 minus sine x, and look what happens. That goes to 1, right? And then you can plug it in, and what do you get? Second? 2. And that's exactly what we got here, too. I think L'Hopital's rule is easier. Especially since you don't remember your trig functions, identities. Okay. So, L'Hopital's rule is pretty straightforward. All right. Or I thought it was anyway. Okay. So, let's move on to example 4. Now, the trouble is, when they gave you the theorem for L'Hopital's rule, they said it works when you're using 0 over 0 or plus or minus infinity over plus or minus infinity. What they didn't tell you is it also works for other indeterminate forms like 0 times infinity. So can I clear this out of the way? All right, thank you. So let's do example 4. What is the limit as x approaches 0 from the positive side, okay, of x log x? Now, why do we say from the positive side only? Yeah, you can't take the log of a negative number. Ever. You can't take the log of 0. Ever. Okay? But you can take the log of a number approaching 0 as long as it doesn't equal 0. From the right-hand side. Okay? That's what the x plus means. Now, that is not a L'Hopital form yet. Okay? How can you make it a L'Hopital form? Okay? Here's one way. I'm not sure this is the best, but it's one way. That's the same as the limit as x approaches 0 from the positive side. You got to have that in there. And this will be a log x over 1 over x. Isn't that the same as x? 1 over x is the same as x, right? Okay, so now is that a L'Hopital form? What is log x approach as you approach 0 from the left? Where's log x going? Let x approach 0 from the right. I said from the left. It's from the right. X approaching 0 from the right. Where's log x going? Second? Okay, the log x is the y value. So it's either going up or down. It's going up, okay? Ooh, up. I may have messed up my log function. Let me think a minute here. Log function is the inverse of what? E. E goes like this. It goes through 0, 1, right? So that means log must go through 1, 0, right? If it's an inverse function. It looks like to me it would be doing like this, right? That's what log looks like. Now, what does that imply as x approaches 0 from the right-hand side? Where is log x going? Negative infinity. Okay? So that would be a negative infinity. And what is 1 over x doing as x approaches 0? It's going to positive infinity. So that's an infinity over infinity form. We can use L'Hopital's rule with that one. Okay? Infinity over infinity, that's okay. Okay? Now, what would we do? What would we do? Anyone? Wait, no, okay. Take a derivative, all right. Okay, what's the derivative of log x? Oh, I thought we were through with those. We didn't have to remember that, did we? Derivative of log x? Say again? E to the x? No, that's the inverse of log x. Nope. What? X to the negative 1. In other words, 1 over x. So this will be 1 over x. Okay, that's the derivative of the numerator. What's the derivative of the denominator? Now, you might want to write that denominator as x to the minus 1 and take the derivative of that, and what do you get? Negative 1 x to the negative 2. Exactly. Now let's write that in rational form, and that would be what? Negative. X minus 2 flips it down in the denominator. Negative 1 over x squared. Negative 1 over x squared. Okay. Now what can we do with a form like that? Back in algebra, you used to call that, the books usually call it a complex fraction. I don't like using the term complex there because usually complex means imaginary numbers. It's not what we mean by that. What we mean by this is a complicated fraction. It's a fraction of a fraction. And what was the technique for solving that, for simplifying that? Anyone remember? Say again? Okay, you will multiply by reciprocal is certainly one way to do it. So that would be the same as the limit as x approaches 0 from the positive side of 1 over x times a negative x squared over 1. Is that what you meant? Okay, I agree. Then you can divide out one of the x's, and that gives us a negative x, right? And what is that approaching when x approaches 0 from the positive side? 0. Okay, that's 0. All right, so to get an idea of what was going on here, if you think about it, as x approaches 0 from the right, this is approaching 0. This is approaching negative infinity. Who wins? The real big negative number or the 0? Well, this tells us 0 wins out. Okay? May not always, but it did win that one. Let's see if they got it right. Look at that. They did. Excellent. Now, they used, and maybe you should have, and maybe that's where you got it, they used the exponential forms of your x's throughout. And so they did this limit here, they say is the limit as x approaches 0 from the positive side of x to the minus 1 over minus x to the minus 2. And then they use the rules for exponents there. What would that give you? Minus x to the negative 1 minus a minus 2 be negative 1 plus 2 would be plus 1. So that gives you that directly. But I didn't know which you preferred doing, so I did it that way. Now let me give you another way. Yours is perfectly correct. Another way you can simplify these, what they call complex fractions. Find the largest denominator. What is it? X squared. Multiply numerator and denominator by x squared. Okay, here the x squareds go out. Here one of the x's goes out, and you're left with a minus x. So there's another way to do it. Every way, correct way, gives you minus x. Then you can take the limit of that. All right. So there we have another form. L'Hopital's rule works if you have 0 times infinity, or negative infinity, or whatever. Okay. Now, I think I want to go to a clean slide. Can I erase this one? Is it okay? All right. Here's example 5. Okay. Evaluate this. The limit as x approaches 0 from either side this time of e to the x minus x minus 1 over cosine x minus 1. What can you do? What would you try first? Plug it in, plug it in. So if you plug in x equals 0 up here, what's e to the 0? 1 minus 0 minus 1. 1 minus 1 is 0. Okay, so your numerator is 0. What is cosine 0? Minus 1 is 0. Okay, you got an indeterminate form, so what do we try next? Want to try the definition of a limit? Please don't. Okay, I don't, so let's not. So what do we use? Okay, L'Hopital's rule. Okay, and what do you get there? E to the x minus 1 over negative sine x. Okay? Now what? Plug it in. And what do you get in the numerator? Really? Say again? 0. Okay, denominator? 0. Oh no, we got an indeterminate form, so we can't do anything else, can we? Yes, we can. What do you do with an indeterminate form? Use L'Hopital's rule. So let's do it again. And that will be the limit as x approaches 0 of e to the x over negative cosine x. Everybody agree? Now what do we do? Plug it in, and what do you get in the numerator? 1 over negative 1. So what is your answer? Negative 1. There you have it. Okay? See how that works? All right. L'Hopital's rule, pretty powerful, isn't it? Do all sorts of stuff there. Okay? All right, for me to erase that one too? Okay. So that one may take a little while. What will you do here? The limit as x approaches 1 of x squared plus 1 over 2x plus 1. What would you do? Plug it in, okay, and what do you get? Two over what? 2/3. You're absolutely right. Y'all, guess what? You didn't let them trap you. The question really was, can you use L'Hopital's rule there? Why not? It has to be an indeterminate form. That's not an indeterminate form. So when you plug it in to check it, that's why I always had you plug in first. So you don't just say, oh, L'Hopital's rule. It's a product, it's a quotient of two polynomials, use L'Hopital rule. No, okay? Always plug in first and see if it's indeterminate. If it's not indeterminate, L'Hopital's rule doesn't work. See, the requirement is that these two have to be 0. They are not. Okay. So no, you would not use it. Okay. If you tried to use it, let's try. Let's imagine, what if we use it? Why wouldn't it work? What would you get there if you had tried to use it? It'd be what? Really? 2x, okay. Over 2? Is that what you said? I couldn't hear. Okay. And then plug in, and what would you get? 1. Is 1 2/3? No. Okay. So therefore, no. Don't use L'Hopital's rule if it doesn't meet the criteria that the numerator and the denominator are either both 0 or both some type of infinity, positive or negative infinity. And we also have seen that if it's a product of 0 times an infinity, that would also qualify for L'Hopital's rule. Okay. Now we're going to run into another one, okay, that will work for L'Hopital's even though it doesn't meet those earlier, I'm sorry, earlier criteria. Okay, and I think that is this one. Okay, evaluate this. The limit as x approaches 0 of 1 minus sine x minus 1 over x. Okay. And what will you do first? Plug it in. So what do you get here? Second? That's 1 over. Sine of 0 is? 0. Okay. 1 over 0 minus? 1 over 0. Neither one of those are indeterminate forms. Both of those are what we call undefined forms. So first inclination would be this thing's undefined, except 1 over 0 does approach positive infinity, and 1 over 0 does approach positive infinity. So you have infinity minus infinity, and now you don't know which infinity is bigger. Okay, there is that. That doesn't make sense. Does that equal 0? Not necessarily. Okay, so guess what? L'Hopital's rule works here too. Okay, but how in the world do you make it work? Well, try this. Let's rewrite that as as one. This is a difference of two fractions. Let's write it as one fraction. What would that be then? What's your least common denominator? X times sine x, right? Now, to get this one to be an x times sine x, what do you have to multiply by? X. If you multiply the denominator by x, multiply the numerator by x. To get this one over here to be x times sine x, what do you have to multiply by? Sine x. And then multiply that by sine x. Okay? So what we have now is, with those denominators in, x minus sine x over x sine x. Okay, and take the limit of that as x approaches 0. Okay? Now we guess what we do. Plug in there, and let's see what we get. If x approaches 0, this is 0 minus, which is 0 over times, which is. Now we have a L'Hopital's rule. So even though that doesn't look like it had any hope at all, get it into a fractional form. Now you've got it into something that will fit L'Hopital's criteria. Okay? And guess what we do with that? What do we do with that? Take the derivative of the numerator and the denominator. And what do you get in your numerator? One. Say again? Plus what? I couldn't hear. Minus cosine x. I'm sorry, I couldn't hear. Okay? Over, what you got to use in the denominator there? What's that? Not chain rule. Product rule, yeah. And what would that give you? X times cosine x plus, second, plus sine x. Is that what you said? All right. Yeah, that's right. Now what would we do? Plug it in, plug it in. So what do you get in your numerator? 1 minus, which is? Okay, numerator is 0. What you get in the denominator? Plus 0, that's 0 over 0 again. Undefined. So what could we do? Do it again. That's an indeterminate form, so keep doing it. So this will be the limit. And here is Jasmine. All right. We're on page 226, chapter 4, applications of the derivative, section 4.5, L'Hopital's rule. Okay? And basically what L'Hopital's rule says is that when you have one of these indeterminate forms, and we've determined this to be, so far, a 0 over 0 certainly is indeterminate, plus or minus infinity over a plus or minus infinity, that's sure indeterminate. We also had a 0 times infinity, or vice versa, plus or minus infinity. That's indeterminate. And on this one, an infinity minus infinity, when we worked it out, we got it as a 0 over 0, so that certainly fits L'Hopital's also. Okay? So, what does L'Hopital's rule say we do if we have an indeterminate form? Take a derivative of both numerator and denominator. And what does that give us? Sine x over, oh boy, what does that give us? Negative x sine x. That's the first times the derivative of the second. Plus, you said 2 cosine x? 2. Okay. And you did that all in your head, or you read it? Okay. Let's do it in let's actually think through it. Okay. What you did here, you have a product rule here, and that would be x times the derivative of the second, so that would be x times negative sine x. The second part of that would be 1 times cosine x, and then you have plus a cosine x, so that gives you plus 2 cosine x. Okay? I was going to say that's pretty clever if you can do that straight in your head. Okay. All right. Now what do we do? What do we do with a drunken sailor? Plug it in, and what do you get in the numerator? 0 over 2. You're absolutely right. What do we do with that? That's equal to 0. You don't need L'Hopital. If that was 0 over 0, do L'Hopital again. It's not. 0 over 2, that's a number. The number happens to be 0. Okay? Got it. Okay. Now, I think that this next example, oh, it is here. Okay. I was thinking it wasn't, but it is. Okay. Yeah. Okay. This is example 8. Here's your function. Evaluate, I can't talk anymore. Evaluate the limit as x approaches, oh, they haven't written it down, so let me write it down. The limit as x approaches 0 from the right, my eyes are doing wacko things again. Yeah, of x to the x. Okay. Well, Houston, we have a problem here. If you try to plug it in, 0 to the 0th power is basically not defined, okay? Because anything else to the 0th power would be I think in any language or situation, that's indeterminate. You can not tell who's winning first and what's the difference. So, goodness. I woke up this morning with a sore throat, and all this talking is not making it any better. What do you think you can do with a problem like that? 0 to the 0th power is something that it's just hard to handle. 0 to any non-zero power is what? 0. Anything to the 0th power is 1, except 0 to the 0th power, which is not defined. So we got a problem, you know. That's not even a defined expression as x is approaching 0. Okay? Is there any way we could make it defined? Here's the trick. Anytime you have an exponential, this is a really bizarre exponential function. What an exponential function is when the variable is in your exponent. Those are types of exponential functions. If it's numbers in the exponents, those are polynomials. If it's variables in the exponent, those are exponentials. Okay, Okay, this has a variable in the base and a variable in the exponent, which makes it a sort of special case exponential function. So how do you simplify an exponential? What's the inverse operation for exponentials? Log. So that's what we're going to do. Let's do this. Now this, you have to be careful when you're doing this. Let's pull this out of the limit for now. X to the x power, if we take the log of that and then do the exponential of that answer, you've got the same thing. You taking something, operating on it with a log, and then operating on it with its inverse, that gives you that same thing again, right? Trust me, okay? That's a legal thing to do. It's sort of like if you give me a number, 1. Give me another number, 2. Let's add 2 to the 1 and you get 3, but then subtract 2 from the 3 and you get 1. You're right back where you started. If you do an inverse operation, you do the operation on the number, then do its inverse on it, you wind up with the same number. Same thing here, okay? Now, what is log x to the x? Rule of logarithm, what would that be? E to the x, log x, okay? All right, 10 o'clock scholar, why do you come so soon? Okay, glad you're here. All right. Angela's here. All right. Finally getting close to a full class. Okay. Since we have some new people come in since I last said it, let me take advantage and say it again. Okay? Your papers are due by Monday, okay? Research papers. I think I've now received maybe 4, or something like that in this course. Pretty small for 11 students. So, if you get them to me today or tomorrow, you still get that bonus point. If you get them to me Monday, there is no more bonus points. If you get them to me on Tuesday or later, you're losing points. So you're right now still in a +1 category. Monday you'll be in you just take the grade category, but then Tuesday and later you're losing points in the negative. You can still get a okay score, but you're going to be losing points on it. Okay. Number 2, Monday. Next time we meet, I'll be returning all your papers to you. Okay? And right now, for the first test, I've received, I'm missing 1, 2, I think 2 students have not turned in the first test. 4, 5, 6, 7, 8, 9. Yeah, 2 students haven't turned in the first test. Monday's the last day to turn that in, and you have to turn it in at the beginning of the time. So if you can get it to me today or tomorrow, I can get it back to you on Monday. I'll try anyway. Second test, let's see. None. I don't have any of those in yet. So please try to get those to me. If you get them to me by today or tomorrow, I'll try to get those back to you on Monday. Okay? But if you don't, if you turn them in Monday, I'll have to give them back to you when you turn in your final. So Monday, we will have class all day long. I'll return. Now, I can't return your research papers. They do ask periodically for samples of student writing, so I can't return those to you, but I will return your tests. But we'll continue and have class, and wherever we end, that's where your final will go up to that point. I'll give you the take-home final before you leave, okay, on Monday. All right, so we got this far with this one. We're on page 226, chapter 4, applications of the derivative, and this is example 8. Okay. Now, that would be one way to approach this problem. I happened to glance at the book, and they're doing it the same way but slightly differently. And let me go on and do it their way, because now that I look at it, it is going to be a little bit faster to go their route. Okay? And here's what they're doing. They're saying, let's let y equal x to the x. That's fine. Okay, and now you take the limit of y as x goes to infinity. I mean, x goes to 0 from the right. Well, before we mess with that, now let's do the log of both sides. This will be the log of y is equal to, and like we just said, that's the log of x raised to the x power, and my rule of logarithms tells us that's x times log x. Okay, so that's what ln y is. Okay, now that's not, we're doing the limit of that function, which is our y, and we took the log of that. So here's another rule, and we did have this before. The limit of a function, which would be log y, okay, is the same as log times the limit of, as x approaches 0 to the right of, and your log y was this thing, x log x. Okay, now, if you recall just a few minutes ago, as in example 4, we already did this limit. Remember? We already did that limit. What did we find that limit to be? The limit of, as x approaches 0 from the right of, I've lost it now, x log x. Okay? We found that to be 0, right? Okay? So what we have here is the limit, is the log of, can't do that. Not the way to go on this one. Okay. All right, they did everything we did except that last little bit there, okay? Everything else was just what we did here. The limit of this is the limit of that is equal to the limit of that, done. And we found out the limit of this was 0. So the limit of log y is equal to, and this is as x approaches 0 from the positive side, the limit as x approaches 0 from the positive side of x log x. And this is what we knew from before to be 0, okay? And that's the limit as x approaches 0 from the positive side of log y, okay? Now, here we go back and take an e of both sides. Okay. It's sort of what I started to do, but I did it in the wrong order. This will be the limit as x approaches 0 from the positive side of e to the log y is going to be e to the 0. Okay? Well, this is, the left-hand side is just y. The limit as x approaches 0. It's not writing there. Yuck. Let me erase this stuff. Alright, let's move it over some. Okay. And this becomes the limit as x approaches 0 from the positive side of y is equal to 1. Well, the limit of y, that's what x to the x, that's what we wanted. So the answer is indeed 1. Kind of a convoluted kind of problem in that you have to take a log function to get it into a usable form, and then ultimately go back to take the e function to undo the log function, but you got to get your steps in the right order. And I started doing that, and I think you could have continued that way, but it looked like the book's way was save some room, but was a little on the weird side there. Okay, so there a form of 0 to the 0th power. You can use L'Hopital's rule on that as well, but you'll need to change that description, so it's in a form you can't use. Okay. They do show the graph of y is equal to x to the x, which is sort of a weird function, I guess. This professor or instructor that we had as an adjunct, I think it was, not important, but seems like he actually used this kind of a technique pretty frequently. Let's move on to example 9. So that was a form 0 to the 0th. You can use L'Hopital's rule there once you manipulate it a little bit. Same thing true with the next one. I don't think we have a graph on it. So let's just clear this out of the way here. And right on here. What if you had a form 1 or some other number to the positive infinity as an exponent? Can you even do that? Well, 1, any other number you couldn't. 1, who knows what's happening? Because 1 to any exponent is 1, but infinity is not an exponent. Any other base raised to infinity is going to be infinity. So, let's take a look at what we get. Find the limit as x approaches 0 of 1 plus 4x raised to the 1 over 2x power. One minus 1 plus 4x times 1 divided by the 2x power. All right. Now, again, that doesn't really fit in any of our little boxes, regular boxes. Goodness, my eyes are hurting. Been losing sleep all week, and that may be part of it, but I was feeling better this morning. But man. Okay. Again, this is a rather bizarre looking form, and anytime you have an exponent in your variable in an exponent, that should suggest to you, let's take a log. So sort of the same thing we did with the last one. Let's start with y is equal to 1 plus 4x raised to the 1 over 2x power. Okay? That's what's inside the thing. First step here is take a log. Log of y is equal to, hopefully by now you know the rules of logarithm, that's 1 over 2x times the log of 1 plus 4x. Everybody buy that? Okay. Now, what we're going to do is take the limit of that log y. Not y, but log y. The only thing that sort of bothers me on this, and I think it'll work itself out okay, is that your x is approaching 0, but neither from the left or the right. And usually when you do a log function, you want it to be from the right. So let's see if this works okay, keeping it this way. This will be the limit as x approaches 0 of, goodness, eye hurts. Okay, let's write it this way. Log of 1 plus 4x over okay. Yeah, over 2x. Okay, that's what I was heading. I was having trouble focusing on it. All right, that's what our thing has become. Now remember, that is limit of log y, not limit of y. You have to remember that. This is limit of log y. All we've done is written this in the numerator and this in the denominator. Okay? Now, does this limit exist? Let's plug it in and see. When x is equal to 0, what is 4x? As x approaches 0, what is 4x? 0. 1 plus 0 would be 1, and log of 1 is 0. Okay, so we have 0 in the numerator. What we got in the denominator? 0. Okay. So what will we do to this? L'Hopital's rule. X approaches 0. Goodness gracious, that hurts. Of what? Derivative of your numerator is? Derivative of a log. The derivative of a log. Second? 1 over the thing. So that'd be 1 over 1 plus 4x. Right? That's the thing in there. But we got a little bit of a chain rule issue. You have to multiply that by 4. Do you see that? Yay or nay? Okay. Then the root of the denominator is? Second? 2. Very good. All right. Can we take the limit of that? As x approaching 0, what's 4x?
0.
Plus 1 is? 4 over 1 is? Over 2 is? 2. So we've got 2. That limit is equal to 2. But that limit was the limit of log y. So we need to take the exponential of that. I'm just going to write exponential of this limit, blah, 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 blah. And that would be the exponential of 2. Well, the exponential of, and this was log y, that would just be, move the e on the inside, and that would be y, the limit then of y, and that would be the limit of this thing, and there's your answer, e to the second. Strange but true. Okay. Now, here's another little kind of application of this. Sometimes we're interested in determining which of two functions, f and g, grows faster. For example, there are two standard computer algorithms for sorting data. Okay? The first is alphabetizing or ordering to rank, okay? And there's others, okay? And there's two different ways of sorting that, alphabetized or ordered according to rank type thing. One is a quick sort and one is a bubble sort, okay? The average time required to sort a list of size m has order of size n, has order of magnitude n log n for the quick sort and n squared for the bubble sort. Which logarithm is faster when the size of n is large? Okay? Although n is a whole number, that problem amounts to the same thing as preparing f of x equal x log x to a g of x equal x squared as x approaches infinity. So even though one is integers, the other is all real numbers, they work the same. Now, we say that f of x grows faster than g of x if the limit of f of x over g of x is equal to infinity. Obvious, x wins. X is the bigger, okay? Or equivalently, the limit of g of x over f of x, and this is as x goes to infinity, okay, I can't write well. This limit would then have to be 0. If f of x is larger than g of x past a certain point, then that limit is going to be going to 0. So, with that in mind then, if we're talking about speed of growth, then here's a nomenclature we use. F of x is a great deal less than g of x. And what that means is, if g of x is, you're comparing these two functions, if f winds up way, way, way smaller than g of x in the long run, then the ratio of f to g is going to be 0, g to f will be infinity. Okay? So, here's L'Hopital's rule. Sorry. It's hard to breathe. Okay, L'Hopital's rule, well, before we get there, obviously for large x's, x squareds get bigger much faster than x, right? Here's x, and here's x squared, okay? For small x's, x wins. But for big x's, x squared stomps the mud out of x, okay? So what we could say is the limit as x approaches infinity of x squared over x would be the limit as x approaches infinity of, well, x will go into x squared, x times, and the limit of that is positive infinity, okay? So, with that said, let's do L'Hopital's rule for limits at infinity. So far, we had only had x going to some fixed number a. Okay. I think I want to erase it off. Yeah. All right. Let's blow this up. Goodness, my head hurts. But mostly my eyes just aching. I don't know why. Except possibly lack of sleep, or it just feels so dry. I guess the room is pretty dry. We haven't had rain in a day or two, so I can't get used to it. Okay, L'Hopital's rule for limits at infinity. Let's assume that f of x and g of x are both differentiable functions on some interval b to infinity, okay, and that g prime of x is not equal to 0 for any x is greater than b. Any x is in this interval. Tells you g prime can't be 0 in L'Hopital rule work, okay, for any x greater than b. If the limit of f of x is x approaches infinity, and the limit of g of x is x approaches infinity, both exist, and either both are 0 or both are infinity, then you can do this. The limit as x approaches infinity of f of x over g of x is the same as the limit as x approaches infinity of f prime of x over g prime of x. Looks just like L'Hopital's rule, except before this was some finite number a, and as you let this, if this was an indeterminate form, take a derivative and go for it. Now we have that these are two functions, that all that's required is f of x and g of x are differentiable on some interval going toward infinity, and that g prime is not equal to 0 for that x greater than b, that endpoint here, any x there. And if f of x and g of x at infinity both exist, and either both are 0 or both are infinite. So you still have that requirement here that this limit, the limit of f and the limit of g at infinity is a 0 or 0 or an infinity over an infinity. That's what it means here. So both of those things still hold. Then you can do this provided the limit on the right side exists. Now if it doesn't, hang it up, it won't work. Similar result for limits as x approaches negative infinity. All the other things are required. Let's see if we can work one example with that before it's time to stop. Here's example 10. Which of the functions f of x is equal to x squared and g of x is equal to x log x, okay, grow faster as x approaches infinity? Who wins as x goes to infinity? Okay, I can't draw a question mark. I don't know why. Okay. Which one's greater as x approaches positive infinity? we're not going to make it. We'll start next time at example 10. I was way too optimistic there. Start next time at example 10. Okay. We almost finished 4-5. Homework exercises here would be any of the odds 1 through 9, any of the odds 11 through 15, any of the odds 17 through, goodness gracious, 53. Either any of the odds 55 through, let's do 55 or 57. Okay? And we'll stop there and pick up the rest of those next time. All right, good deal. Okay, and again, next time, let's just look ahead. Need all your papers in by the first of class on Monday. I will be returning all your first test first of class on Monday. I'll need all your second class test in by first of class on Monday. And let's see, what else? Then we'll finish L'Hopital's, that's 4.5. We'll do 4.6, which is a pretty short section. I think we're going to have to skip 4.7. It's sort of a fun thing, but I don't believe we're going to have time for it. And I want to at least introduce you to Newton's method. It's such a powerful, powerful thing, and it's a very short section, so I hope to have a chance to do that. And that's it. And then if there's any time at all, I want to introduce you to the integral. We should have gotten there, but since we lost at least 3 Mondays this term, that cut us short by a week and a half out of a 10-week term. That's pretty significant. We're going to it'll be a rush job on the integral if we get there at all. Now, I know y'all are going back to, some of you are going back to your institutions, and they're probably going to expect you to know a little bit more about the integral than what we're going to have time for. So what I would say, follow up yourself. I think you have all the tools you need to continue the first part of Chapter 5. Usually Cal 2 begins somewhere around substitution. So you got to know a little bit more about integration. What integration is taking an antiderivative. So if I have to leave off Newton's method or just do a slideshow on it, I'm going to try to get you at least into familiarization with the integral. And I believe that most of the time they start on techniques of integration, which to me includes substitution. But hopefully you won't be in too bad a shape. Sorry if you are. Too late now to do much about it. All right, any questions?